Welcome back, and we introduced the idea of implicit functions and implicit differentiation in the last video. Now we're just going to get some more practice. So we're going to look at the Philem of Descartes. Interesting function that, or I shouldn't say function, it isn't a function, but an interesting relationship between two variables that you actually see pop up a lot of the time in algebraic geometry. Some very interesting things that you can talk about with this curve. Nevertheless, our skill right now is to differentiate it and explicitly find the tangent line at the point 3, 3. And if you want to graph it, it ends up being right there. So our line should look something like that. Okay, and we could probably find that using just normal geometry here, but we want to find it precisely. Okay, and then also we want to find where the tangent line is horizontal. Okay, so two different tests, tangent line and also where the tangent line is horizontal. Okay, so to engage in this process, I have the point for the tangent line. I need the slope. Okay, well the slope is dy dx. So I need to find the slope, and I'm just going to write this as goal, which is dy dx. All right, well, we know to find dy dx, we have to differentiate this. Okay, now I'm going to engage in implicit differentiation, so I'm going to apply the ddx operator. I'm going to differentiate both sides with respect to the variable x. So I'm looking at the change of each of the variables in terms of x, because that's what the slope is. So if I differentiate, oops, I forgot the x on the left side. There we go. Okay, so if I differentiate the left-hand side of the equation, again, maybe I'll just write it out, ddx of x cubed plus ddx of y cubed is equal to ddx 6xy. Okay, differentiating the first one, I get 3x squared and then dx over dx. Okay, if you don't want to write that, you don't have to. The next one, I can differentiate y cubed as normal, so 3y squared. But then I have to remember, okay, I differentiated y, it's not x, so I need to write dy dx by the chain rule. Okay, right-hand side is a little interesting. It actually ends up being a product rule. So I'm going to say like 6x is my first function and y is my second function. So according to the product rule, it would be 1 d2, so I differentiate y, just 1, but then with respect to x is dy dx by the chain rule, and then plus 2 d1, so derivative of 6x is just 6. Alright, and with all this I still need to find dy dx, so let's engage in a little solving just using our algebra skills. Okay, so get all the terms with dy dx to one side, all the non-terms, or the terms without dy dx to the other side. I'm going to move this one over, so I believe I get, if I pull out the dy dx as a common factor, there's going to be 3y squared from this first term, and then I'll have a minus 6x as well. And then on the right side, I'll have 6y, and then minus, oops, I'm sorry. Actually, we're okay. I thought for a minute that this dx was dy dx, but remember that's just 1. Okay, and then minus 3x squared. Okay, and we can solve for dy dx by undoing the multiplication by division. So dy dx is equal to 6y minus 3x squared over 3y squared. I should say that's a y, not a g, minus 6x. Okay, and then, so this is great, and then I'm just going to say dy dx evaluated, this is notation, at x comma y is equal to 3, 3. This is notation you will see. This just means take the derivative evaluated at this point, and we end up getting minus 1. Okay, so I'll let you confirm that on your own time. But all of this is to say that our tangent line is in point slope form, y minus 3 is equal to negative 1, x minus 3. Okay, because I have the 0.33 and then the slope of minus 1. Okay, so objective 1 has been done. I found the tangent line at the point, and it seems to match somewhat with the graph, at least based on my initial sketch. Alright, second part. I want to find where the tangent line is horizontal. Okay, well, if the tangent line is horizontal, what do I know about the derivative? Well, the tangent line would have to have a slope of 0, meaning that the derivative is 0. So then this is 6y minus 3x squared over 3y squared minus 6x, as I found above. So if I solve this, the denominator would multiply out. Okay, and I would end up with 0 is equal to 6y minus 3x squared, and moving things around here, I'd have 6y is equal to 3x squared, and y is equal to 1/2 x squared. Okay, so I need to find the points though, right? I know the relationship, I know what y is in terms of x, so now I need to look at my original function, which was x cubed plus y cubed is equal to 6xy. And I want to substitute this into that relationship. Okay, so then I have 1/2 x squared cubed plus 6x, and then 1/2 x squared. Okay, so I have x cubed plus 1/8 x to the 6th is equal to 3x cubed. Okay, so then I can rearrange this and solve. I end up with, let's see, I could factor out an x cubed after I move the 3x over, and then I'd have 1/8 x cubed minus 2 is equal to 0. Okay, so then the solutions from this, I either get that x is 0, or from this, I would get, move 2 over, multiply by 8, 16, so x would be the cube root of 16. Okay, which is the same as 2 4/3. Okay, you would need to find the corresponding y value because it does ask for the points. So when you do that, you get y is equal to 0, and then for this one, you end up with 2 to the 5/3. Okay, so these would be your points where the tangent line is horizontal. All right, all of this is stemming from this nice volume of Descartes, okay, where we had to find the slope, dy dx, by using implicit differentiation. So when we differentiated using the chain rule, anytime you're differentiating something that is not the variable of interest, you need to allow for dy dx, dy dt, dx dt, something indicating that you're differentiating a variable other than the variable of interest.